Hello, this is Part C of the Chapter 9 lesson. In Part C, we're going to talk about an idea called multiple regression, which sounds kind of scary, but it's really not a whole lot different than what we did in Part B of this lesson. Multiple regression has the same basic idea as linear regression. The only difference is that there's going to be more than one predictor variable. There's still going to be just one response variable, but we're going to have more than one predictor variable. And we're going to get a regression equation that looks very similar to what we had in Part B, except that there's going to be more terms. So we're going to have our response variable equals a constant plus another constant times our first predictor variable plus another constant times our second predictor variable plus another constant times our third predictor variable plus so on and so forth. So one term for each predictor variable. And so to illustrate this idea, let's look at example 9.3 from the Excel guide. And specifically in this example, we want to find the multiple regression equation that predicts systolic blood pressure in terms of age and sex. So we're going to use the same data as what we used in examples 9.1 and 9.2. It's just that we want to, our response variable is going to be systolic blood pressure, and our predictor variables are going to be age and sex. And so a regression equation is going to have this general form. Systolic blood pressure equals a constant plus a constant times age plus another constant times sex. So our data, again, use this worksheet regression from the Chapter 9 workbook. It's the exact same data that we used in the other examples. Here's the data for our systolic blood pressure, and then here's the data from our two predictor variables. Notice that those two columns are right beside each other. Whenever we do multiple regression in Excel, we have to make sure that all of our predictor variables are in columns right next to each other. And that's the case here already. And so doing the multiple regression calculations are just like doing single regression calculations like we did in Part B of this lesson. Go to the Data tab and then Data Analysis and then select Regression, press OK. And you're going to format the window so it looks like this. Your Y range are the values of your response variable. And then your input X range is the range containing values of your predictor variables. In this case, the response are in column D, the predictors are in columns A and B. So you just select that whole range. Select Labels, and then select any blank cell for the output range. I selected cell K1, but there's nothing special about that cell. Press OK, and you'll get the same set of outputs that we got from Part B of this lesson. We're going to focus on just the last part of this, which gives specifically the coefficients. We'll talk about the p-values here in a minute. But here's the values of my coefficients. This is my intercept. This is the coefficient of age. This is the coefficient of sex. And so our regression equation would look like this. Systolic blood pressure is 87.2 plus 0.52 times age plus 5.38 times the sex. And so if I could use this to predict systolic blood pressure if I know the person's age and the person's gender. Remember then this data 1 represents a male and 0 represents a female. And so that's all there is to calculating a multiple regression equation. And now let's talk about these p-values over here. We can interpret these p-values in the same basic way as what we did in Part B. Remember that a small p-value means that coefficient is significant. A large p-value means that it's not significant. So if we look at the p-value for the intercept, we see a scientific notation there. It means we've got a very small p-value, so the intercept is significant. Then we look at the next one, age. That p-value is also small, less than 0.05, so that is significant. But now if we look at the last one, sex, that p-value is rather large, and so sex is not a significant predictor of systolic blood pressure. And so we again interpret these multiple regression results just like we do with single regression results as we did in Part B. Now let's look at an example 9.5 from the textbook. And one thing this example illustrates is that often in journal articles and other places, the author doesn't give all the data that are used to calculate the regression analysis. All they give is the results. And so in this example, the question is there a relationship between systolic blood pressure and body mass index? And so the data that they use in this textbook, or in this example, comes from a sample of 3,539 people. So obviously they can't list all that data in one place very conveniently, and so they don't list it at all. All they give are the results. And so one result that they give is the regression equation, which is calculated just like what we did in the previous example. And so systolic blood pressure, there's the intercept, and here's the slope, 0.67 times the body mass index. Now let's make an observation. This coefficient is positive, and so as we saw in one of our previous examples, a positive coefficient is significant. That means that if this variable increases, then this variable over here is also going to increase. So specifically, that means that a higher body mass index is going to lead to an increased systolic blood pressure. Now, keep this value 0.67 in mind, because we're going to see that value here in a bit again. And so, follow-up question that we might ask is, well, is the body mass index a significant predictor of systolic blood pressure? This coefficient is positive, and that's significant, or that appears to be significant, so, but is it really significant? Well, we can answer that by looking at the associated p-values, and so those p-values are given in this table 9.7, titled Simple Linear Regression Analysis, where the dependent variable is systolic blood pressure. This result looks very similar to what we see from Excel. We see our intercept, our coefficient of the body mass index. Here's our test statistics for the associated hypothesis tests, and here's the p-values. Specifically, we're interested in this one right here, which is small, and so that means that body mass index is a significant predictor of systolic blood pressure. Or stated in other words, the association between body mass index and systolic blood pressure is statistically significant. And then we often give the p-value in parentheses like that. Okay. Well, now another follow-up question we might ask is are there some potential confounders? Specifically, are age, gender, and treatment for hypertension potential confounders? And so for each one of these 3,000 people in this sample, we recorded their systolic blood pressure, their body mass index, their age, their gender, where like in the previous example, a 1 will stand for male, a 0 stand for female. And then we also record is the person taking treatment for hypertension, where a 1 will represent that the person is taking a treatment and the 0 does not. And so we can do a multiple regression analysis, and those results are shown here in this table 9.18. So the dependent variable again is systolic blood pressure, and so we've got an intercept, we've got a BMI as one variable, age as another variable, gender as a third variable, and then treatment for hypertension as a fourth variable. And so they calculated these regression coefficients just like we did in our previous example. And so putting these together, we could get our multiple regression equation that says systolic blood pressure is our intercept plus 0.58 times BMI plus 0.65 times age plus 0.94 times male gender times 6.44 times treatment. Okay. And so now that doesn't answer our question, are they potential confounders? We'll answer that question by looking at our p-values. We're going to interpret these p-values just like other p-values for regression analysis. A small p-value means that that variable is significant. A large p-value means that that variable is not significant. So this p-value is small, this is small, this is small, this is large, this is small. So it looks like everything is significant except for male gender. So all variables are significant predictors of systolic blood pressure except for male gender. Okay? And so that means that age, treatment for hypertension are confounding variables. Okay. Now let's make an observation here about that coefficient of body mass index. Remember, the original question was, is body mass index related to systolic blood pressure? Well, when we did our single regression analysis, where we only considered body mass index as our predictor variable, we got a coefficient of 0.67. When we included these other variables, we got a regression coefficient of 0.58. So we went from 0.67 to 0.58. That's a decrease. Specifically, that's about a 13% decrease in the value of that coefficient. And so we would interpret this by saying that after adjustment for age, gender, and treatment for hypertension, body mass index is less significant. So this less significant simply means that the value of our coefficient dropped. Okay. So our conclusion that we'd reach based off of this analysis is that part of the association between body mass index and systolic blood pressure is explained by age, gender, and treatment for hypertension. So in other words, it looks like age, gender, and treatment for hypertension are indeed confounders. Body mass index is not the only variable that affects systolic blood pressure. Okay. So to kind of summarize what we just did here in this example, we used what the book simply calls an informal rule. And the goal of this informal rule is to determine if a set of predictor variables are confounders on a given predictor variable. In this case, our given predictor variable was body mass index, and then our other set of predictor variables was gender, age, and treatment for hypertension. And so what we did here was, first step was we found the regression equation in terms of the given variable. So we found that regression equation that gave systolic blood pressure in terms of BMI all alone. And then we found the multiple regression equation in terms of all the variables. So we had all four of our variables there. And then we compared the coefficient of the given variable from the first equation to the coefficient in the second equation. So if the coefficient of the given variable in step 2 is more than 10% different than the coefficient in step 1, then conclude that the set of variables are confounders. And that's exactly what we did. In step 1, we got a coefficient of 0.67 for BMI. In the second equation, we got a coefficient of BMI equal to 0.58. That was a 13% decrease. 13% is bigger than 10%. And so we concluded that the set of variables are confounders. And so this just illustrates one use of multiple regression to try to determine whether or not some variables are confounders.